All right, welcome everyone to today's intensive review explainer. We're going to completely demystify Chapter 8, Internal Convection, right in time for your thermodynamics exam. Look, if you're an undergrad engineering student staring at a totally tangled mess of heat transfer equations and wondering where to even start, you are in exactly the right place. Just take a deep breath. We're going to strip away all the confusion today and focus purely on the core concepts you need to absolutely ace this test.
Okay, so here is our game plan for today. We'll kick things off with a welcome to internal convection, dive into the core energy balance, map out the two thermal boundary conditions, constant surface heat flux and constant surface temperature, and finally, we'll wrap up with a foolproof problem-solving playbook. Let's get right into it.
Welcome to internal convection. To start off, let's just anchor ourselves on the big picture goal of this entire chapter. What are we actually trying to do here? Well, we're figuring out exactly how much heat is added to or removed from a fluid as it flows through a pipe. That's literally it. Whether it's oil in a massive pipeline or just the coolant in your car's engine, that is our singular mission today.
Just picture a basic control volume of a tube. You've got fluid flowing in at an initial inlet temperature, it moves through the pipe, heat gets added from the outside, and then it exits at a higher temperature. The physics rule governing this is beautifully simple. The heat transferred to that flowing fluid, it's exactly equal to the increase in the energy of the fluid itself.
Moving to Section 2, the core energy balance. Now, if you remember only one thing for this exam, please make it this universal truth of internal convection, the general energy equation. Before we even start worrying about what the pipe wall is doing, we have to respect this foundational balance.
What's really interesting here is how straightforward the core math actually is once we break down the variables. Q is just your total heat transfer rate, and that equals your mass flow rate, which is how much fluid is pushing through, multiplied by the specific heat of your fluid, multiplied by the temperature change from the exit to the inlet. As long as there's no extra work being done inside that control volume, like from a pump or a fan, this basic energy balance is your unbreakable starting point for steady flow.
Section 3, two thermal boundary conditions. Okay, here's where students usually get tripped up. Entering the tube, we basically hit a fork in the road. In an internal flow problem, everything is incredibly sensitive to the specific conditions happening right at the pipe wall. You have to know which reality you're operating in before you can even think about choosing your equations.
So think of it through these simple analogies. Constant surface temperature is kind of like having boiling water or condensing steam on the outside of your pipe. No matter what happens, the wall of that pipe is locked at a fixed temperature. On the flip side, constant surface heat flux is like wrapping an electric resistance heater tight around the pipe. The temperature of the wall itself might get hotter or colder, but the sheer amount of energy being blasted into the fluid per square meter, that is totally uniform and constant.
And here's the absolute crucial point to remember. You can only ever have one of these conditions at the surface, never both at the same time. When you sit down at your exam, the very first thing you need to do when reading a problem is hunt for the clue. Is the temperature locked or is the heat flux locked? Do not proceed until you solve that mystery.
Section 4, constant surface heat flux. Let's head down that first path, where the heat being added per unit area is completely uniform across the entire length of the pipe. Honestly, this is usually the more straightforward path on the exam. Because we're pumping a constant, steady amount of heat into the fluid every single inch it travels, the mean fluid temperature rises perfectly linearly from the inlet to the exit. And since the local heat transfer coefficient stays constant in the fully developed region, the surface temperature of the pipe rises perfectly linearly too. This means that the gap between the wall temperature and the fluid temperature remains exactly the same all the way down. And because everything behaves in these nice, predictable straight lines, you get to use straightforward linear algebra to find your exit fluid temperatures and final heat transfer rates. You basically just take your heat flux, multiply it by the surface area to get your total Q, and boom, you can easily solve for the exit temperature. It's clean, it's linear, and it's super approachable.
All right, Section 5, constant surface temperature. Now let's shift gears to that second boundary condition. This is where the wall temperature doesn't change at all. Imagine a pipe fully submerged in an ice bath. This one requires just a little bit more mathematical finesse.
Now, a lot of students get tempted to just use the arithmetic mean here, which is just averaging the inlet and exit temps. But be careful. It's a simple approximation, and built right into it is the assumption that the fluid temperature varies linearly. But as we literally just discussed, that linear rise only happens with a constant heat flux. With a constant surface temperature, a linear variation is practically never true. It is a massive trap you need to avoid.
The actual temperature profile tells a totally different story. Let's say your pipe wall is locked at 100 degrees, and your fluid enters at 20 degrees. Heat transfers super fast at first, right? Because the temperature gap is huge. But as the fluid warms up to 50, then 70, then 90 degrees, that gap shrinks, so the rate of heat transfer slows down. The fluid temperature doesn't rise in a straight line at all. It curves asymptotically, getting closer and closer to the surface temperature as it travels, but never quite touching it.
Because of that asymptotic curve, the temperature difference between the fluid and the surface actually decays exponentially in the flow direction. So to find your exit fluid temperature in this specific scenario, you have to respect that decay. You'll use an exponential relation, one that factors in the heat transfer coefficient, surface area, mass flow, and specific heat, to calculate that exit temperature accurately. To accurately calculate the total heat transfer rate here, you absolutely must use the log mean temperature difference, or LMTD. Like I said, the arithmetic mean is a trap. The LMTD safely and rigorously accounts for that exponential decay we just talked about. And honestly, the best part? It's practically fail-safe. Whether you're heating up a cold fluid or cooling down a hot one, the LMTD formula always guides you to the exact correct temperature difference to plug back into Newton's law of cooling.
Section 6, Problem-Solving Playbook. Okay, let's bring all of this theory together into a concrete battle plan for your test. You know the physics now, so let's talk execution.
Just follow these 3 sequential steps for every single problem and you'll never apply the wrong formula. Step 1, read the prompt carefully and identify your boundary condition. Step 2, visualize the temperature variation. Are we talking about a straight linear slope or an asymptotic curve? And step 3, pick your tool. If it's linear, basic algebra works perfectly. If it's an asymptotic curve, you immediately bring out the LMTD.
Let's see how this plays out in 2 really common scenarios you'll likely face. Example 1. You're told a pipe is wrapped in an electric heater. Bam! Step 1, constant heat flux. Step 2, linear rise. Step 3, simple algebra. Okay, example 2. The prompt says the pipe runs through condensing steam. Bam! Step 1, constant surface temperature. Step 2, asymptotic curve. Step 3, you write down the LMTD equation. Memorize this logic map and I promise you cannot fail.
So as you prep for this exam, I want you to ask yourself not just how to solve these equations, but how mastering this logic is going to empower you to design way better thermal systems out in the real world. Every single power plant, EV battery, and aerospace cooling system relies on engineers who know precisely how to manipulate these 2 boundary conditions. So study hard, trust the energy balance, and I will see you next time on The Explainer.